Hi, welcome to your Unit 2, Lesson 2 notes. Today we're going to be looking at change in linear and exponential functions. Goals for today's notes would be to be able to construct functions of the real numbers that are comparable to arithmetic and geometric sequences, describe similarities and differences between linear and exponential functions, and solve real-world applications using arithmetic and geometric sequences. So let's look at the relationships between linear functions and arithmetic sequences. We know that a linear function of the form y equals mx plus b describes a continuous function whose domain and range is all real numbers. The y-intercept is the point 0b, and the rate of change of the function is the value of m, which represents the slope of the line over its domain. Arithmetic sequences can be represented by linear functions, which we noticed last lesson. However, sequences and their corresponding functions may have different domains. So looking here at example 1, we're going to use the graph of the sequence shown on the right to complete the table below. So we have the point 1, negative 5. We have the point 2, looks like it's at negative 3. Get into red here, negative 3. At 3, my y is negative 1. At 4, my y is 1. 5, we're at 3. 6, we're at 5. So I'm just pulling the ordered pairs from there. So looking at the common difference, so our common difference D is going to be equal to, it looks like we're adding 2 each time. So going back up here, if my first term in my sequence is negative 5, and I have a common difference of 2, my 0 term, my A naught, would end up being negative 7, because we're going to do negative 5 minus 2, which gets us to negative 7. Okay, so find the difference, write an explicit rule for A sub n. So A sub n is equal to my common difference, 2, and my A naught minus 3. Use this information from part B to write a linear function. So now we're just going to turn that into a function term in terms of n. So f of n is equal to 2n minus 7. I could have, up here for this one, I could have instead worked with the first term, right? And I could have done a sub n is equal to negative 5 plus n minus 1 times my common difference, which is 2, which then would simplify to our one with the a naught, right? Okay, moving on. So example 2 says, given the arithmetic sequence where a sub 1 equals 17, a sub 8 equals negative 39, state the domain and the range of the sequence. Well, we just said that an arithmetic sequence is the same as a linear function. The common difference is your rate of change of that linear function. Rate of change is also known as the slope of a linear function. So all we need to do to find the common difference is to find the slope, right? So to find the slope of those two terms, do our outputs minus each other. So negative 39 minus 17 over 8 minus 1 gets me negative 56 over 7, which tells me my common difference is 8. So from 17 minus 8, that puts us at 9. Minus 8 is 1. Minus 8, negative 7. Negative 15. Negative 23. Negative 31. So my domain is all of my n values that I used in this sequence. So 1, 2, 3, 4, 5, 6, 7, up to 8. The set of those numbers. My range is the set of the values of 17, 9, 1, negative 7, negative 15, negative 23, negative 31, negative 39. Right, because it's specific to the sequence. It's not every single number falling on that function, so it's a discrete function as opposed to a continuous function. Example 3, write a linear function whose domain is all real numbers that will contain the domain of the sequence in example 2. So your steps for writing the functions. All right, so if my first term we're saying is 17, and my common difference is negative 8, then my a naught is going to be 17 minus negative 8, which gets us to 25. And remember, a sub n is equal to my common difference, n plus my a naught. Just turn that into function notation. So f of n is equal to negative 8n plus 25. So now we're going to get into the explicit formula. And we've been doing explicit formulas pretty much this whole time. So it denotes the nth term of the sequence where n tells the term's location. It defines the sequence as a formula in terms of n. We can either write it in subscript notation like a sub n, or we can use it in function notation f of n. So we're going to do it for both in example 4 here. So here we're given a sequence of 32, 27, 22, 17, 12, and 7. So we want to find an explicit formula in both subscript notation and function notation. So looking at our ordered pairs, at x equaling 1, my output's at 32. Looks like 2, I'm going to estimate that to be around 27. 3, I'm going to put it around 22. 4, my output's around 17. 5, I'm going to say 12. 6, I'm going to say 7. So we have our first term, second term, third term, fourth term, fifth term, sixth term, and then our a sub nth term. If we did it in function notation, it'd be f of 1, f of 2, f of 3, f of 4, f of 5, f of 6, and then f of n. All right, so we just have our two different notations happening here. We have it in subscript, we have it in function. So let's write out the rule of what's happening. So if my first term is 32 and my common difference looks like we're subtracting 5 each time, so minus 5, then my a naught is going to be 32 minus negative 5, so 37. So my subscript notation is a sub n is equal to my common difference, negative 5, n plus my a naught. Function notation, f of n is equal to negative 5n plus 37. Simple enough. Okay, welcome to example 5. So here we are given an explicit formula for our sequence, 9 minus 3 times the quantity n minus 4. And we want to find the first 10 terms. So we can either just use that formula. Me personally, I would just simplify it because then it'll be easier when I go to evaluate. So 9 minus 3n plus 12, which would get me to negative 3n plus 12 plus 9 is what, 21. So now when I evaluate it, it might be a little bit easier. So when I plug in 1, negative 3 plus 21 is 18. Plugging in 2, negative 6 plus 21 is 15. Plugging in 3 would get me an output of 12. Plugging in 4 would be 9, which now I can see it's just going down by 3 each time, right? Because that's my slope or my rate of change, which is my common difference. So 6, 3, 0, negative 3, negative 6, and I think we end with a negative 9. So now if I wanted to find the 200th term, I could just do negative 3 times 200 plus 21. That evaluates out to negative 579. Write the slope-intercept form. Well, I already kind of did that up there. F of n is equal to negative 3n plus 21. Elizabeth waters her vegetable garden using water that she collects in her rain barrel. Okay, example 6. Elizabeth waters her vegetable garden using water she collects in a 55-gallon rain barrel. On May 3rd, the barrel was full of water, and on May 8th, the barrel contained 47 gallons of water. So that means we're starting out with 55 gallons on May 3rd. I don't know what I have on May 4th. I don't know what I have on May 5th, May 6th, May 7th. But on May 8th, I know that I have 47 gallons left. So we need to figure out what the common difference is between the two, right? which is the same as finding the slope. So this is 1, 2, 3, 4, 5, 6. My common difference is going to be equal to 47 minus 55 over 6 minus 1, which is negative 8 over 5, which is negative 1.6. So if I lose 1.6 gallons each day, then my second day, or May 4th, would be 53.4, then 51.8, then 50.2, then 48.6. And then we'll be down to 47 gallons, right, on May 8th. So write an explicit rule using both subscript notation and function notation. So if my A1 is 55 and my common difference is negative 1.6, then A naught is going to be 55 minus a negative 1.6, which is 56.6. So A sub n is equal to my common difference, negative 1.6 n plus my A naught, 56.6. Function notation, f of n is equal to negative 1.6 n plus 56.6. Explain when the rain barrel will be empty. Assume there is no rain in the next 10 days. So we want to figure out what value of n would put me at 0, right? So remember, these are my n's. These are my outputs. So I want to figure out when negative 1.6 n plus 56.6 will equal 0. So solving that out gets me negative 56.6 equals negative 1.6 n. Divide. Gets us n is about 35.375. So I would say something like on day 36, which day 36 from May 3rd would be June 8th. The barrel will be empty. Okay, example 7. Alan is assigned a book to read for his biology class. Counting today, Monday, as the first day, he finds that he must read through page 385 by day 12 and through page 665 by day 20. So to me, that's telling me that he probably needs to make sure by the beginning of day 12, he's walking into his biology class and having page 385. So that means on day 11, technically, is when he should have finished his 385, is what I'm going with. We're going to be proactive, right? And then if he needs to have read 665 by day 20, then by the day 19's end, he should have been at 665. Okay, so we need to write a rule for the nth term of the arithmetic sequence that represents the number of pages that he will have read after n days. We're going to use this function. So in order to find our common difference, it's going to be the same as our slope. So 665 minus 385 divided by 19 minus 11 gets us 35. So A sub n is equal to, now I don't know my A naught. I could figure it out, but let's let n equal 19 and k equal 11. Oh no, we don't need to do that because we already know what our rate is. Let's let n be n. Let's let k equal 11. So A sub n is going to be equal to our A11, which is 385, plus my common difference of 35 times n minus 11. So there's a rule. We could simplify that. So A sub n equals 385 plus 35n minus 35 times 11 is 385, which gets us A sub n is equal to 35n, which is interesting that my y-intercept is 0. Makes sense. At day 0, we'd be at 0 pages. So what's the common difference? What does it mean in terms of Alan's assignment? So our common difference is 35, which means that Alan needs to read 35 pages per day in order to complete the assignment. In order to complete the assignment. Based on your formula, how many pages does Alan need to read today on Monday? Explain how you know this. Well, since he needs to be at the page 385 on day 11, he should read 35 pages today, right? So, because 35 times 11 would get us to 385. So, Alan needs to read 35 pages today. To be at 385 on day, or let's say by day 12. So then using your function rule, how many pages will Alan have read by Friday's class? Okay, so today is Monday, Tuesday, Wednesday, Thursday, Friday. So he's doing, 35 pages each day. So for part D, using your function rule, how many pages will Alan have read by Friday's class? So that means he needs to have it done before Friday's class. So he's going to read 35 pages on Monday, 35 pages on Tuesday, 35 pages on Wednesday, and then 35 pages on Thursday. Then he will go to class and he'll have read a total of 140 pages. So by Friday's class, Alan would have read 140 pages. So he would have 4 days to read prior to that class on Friday. Okay, here is the beginning of lesson 2, unit 2, part B. So now we're going to look at this geometrically, right? So we've seen that when the output values of a function change at a constant rate, the function is linear. Now let's look at what happens when the output rates change proportionally. When your sequence is geometric, the rate of change will increase or decrease as the value of n increases, right? So as n is getting larger, our rate of change is going to get larger, or it's going to be getting smaller. So use the graph of the following to shown on the right to complete the table. So at 1, it looks like we're at 64. 2, they're saying we're at 32. At 3, I'm going to estimate we're at like 16. We want to make our numbers look nice here. You can see where I'm going. 4, I'm going to say 8. 5 is 4. 6, 2, 7 is 1. So what's the common ratio happening? That one's an easy one to see. We're taking half each time. So my explicit rule that we learned about last class, start with our first term, 64, times my common ratio of n minus 1. Or if you want to go to the a naught, right? Well, what number do I have to take half of to get to 64? Or doubling 64 would put me at 128 would be the 0 term, which would be 1/2 to the n. Both are acceptable answers. I'm just putting them there for you so you have both. Use the information from part B to write an exponential function that corresponds to the nth term. So we're just going to turn this into function notation. So f of n is equal to 64 1/2 n minus 1, or f of n is equal to 128 1/2 n. Given the geometric sequence, we're given a first term of 144. Our third term is 36. We want to state the domain and the range of our sequence. So again, remember, we don't know what our common ratio is, but we can find it by finding that geometric mean. So if you don't remember that we're just taking the product and square rooting it, we could set up our proportion. So a sub 1 over 144 should be the same as 36 over a sub 1. A sub 1 squared is equal to whatever 36 times 144 is. Square root. So, sorry, not a sub 1, a sub 2. We're finding a sub 2. Okay, let's move on to example 9. Given the geometric sequence, we're given a first term of 144, third term of 36. We want to state the domain and range of the sequence. So we need to figure out, we have all the domain, right? We have 1, 2, 3, 4, 5, 6, 7. We do not have the range. We have some blanks there that we need to figure out. Let's first start with finding the second term. To do that, we need to find the geometric mean, which if you remember, your geometric mean is just the square root of A1 times A3 or A2 times A4, right? You have that blank in there to get the middle term. If you don't remember that, just set up your proportion. So we know that the second term over the first term should be the same ratio as the third term over the second term, which would then get us to A sub 2 is equal to 36 times 144, square rooting both sides. Tells me my common ratio is 72, or not, my common ratio is not 72. My second term is 72. So then how do I go from 1 to find our common ratio? Well, we'll just do 72 divided by 144, which 72 divided by 144 gets us 1/2. So we're taking 1/2 each time. So half of 36 is 18, half of 18 is 9, half of 9 is 9/2. Half of 9/2 is 9/4. So my domain is the set of 1, 2, 3, 4, 5, 6, 7. And then the range of this sequence is 144, 72, 36, 18, 9, 9/2, 9/4. So write an exponential rule or an exponential function whose domain is all real numbers that will contain the domain of the sequence. So in example 9, we had a discrete function with our sequence. So now we're going to turn it into a continuous function so that our domain is all real numbers. So f of n is equal to my first term times my common ratio, which is 1/2, to the n minus 1. Or if we want to take it to the a naught, so I need to figure out what number do I take half of to get to 144, or doubling 144 would be 288 times 1/2 to the n. Would be using my 0 term to start. Okay, so now we're going to do the same thing as we did with the arithmetic in example 11. We're just going to take it to the explicit form. So remember, our explicit form is going to be either your g naught times r to the n, which sometimes as a function, we've seen that as a times b to the x. Or if we don't have the first or the second term, we can start with whatever term we want. So we just need to make sure in that exponent we do our n minus our k, which graphically it corresponds to this function right here, y sub 1 times r to the x minus x sub 1, based on a known ratio and your point that you have of x1, y1. All right, so let's put this into play. So example 11, we're given a graph. Let's find our ordered pairs. So 1, 3, I'm going to say we're at 2, 6, 3, 12, 24, 48. Hopefully you can see the pattern by now. We are doubling it each time. This is my second term, which is the same as f of 2, third term, which is the same as f of 3, fourth term, which is the same as f of 4, fifth term, which is the same as f of 5, sixth term, which is the same as f of 6, and then our a sub n term, which is the same as f of n. So in subscript notation, it'd be a sub n is equal to my first term times 2 to the n minus 1. Or if you wanted to knot it, a sub n would be equal to 3/2 times 2 to the n. function notation, f of n is equal to 3 times 2 to the n minus 1, or f of n is equal to 3/2 times 2 to the n. Oops, sorry, that should, yeah, nope, I did that right. There we go. I'm not losing it. Example 12, given the explicit formula for the sequence, write the first 6 terms in the sequence. So that's just plain old evaluating. When we plug in 1, I get 0. Anything to the 0 power is 1 times 6 is 6. Plugging in 2, 1/2 to the 1 power times 6 is 3. Then we get 3/2. Then we get 3/4, because what am I doing? I'm just taking half each time, so 3/8 and 3/16 would be your first 6 terms. Find a naught. So my a naught would be equal to my 6 times 1/2 to the negative 1 power, because 0 minus 1, right? Which is same as 6 times 2. So a naught is equal to 12, or you could just think backwards, right? What would this have to be? It would have to be 12 divided by 2 to get to 6. So let's write our exponential form in function notation. So f of n is equal to, we can either do 12 times 1/2 to the n, or f of n is equal to my first term, which is 6 times 1/2 to the n minus 1. Both are acceptable. Both will get you the same results. All right, let's finish with our 2 application problems. Example 13, Tim released a helium balloon that rose 200 feet in the first minute. In each succeeding minute, the balloon rises only 50% as far as it rose in the previous minute. So it's cutting by half each time. Write a general formula, a sub n, that gives the number of feet risen during the 9th minute of the balloon for the time in the air. Okay, so my initial height is 200 feet. And then its balloon is rising only 50% as far as it rose in the previous minute. So it's taking half away to the n minus 1 power. So now we can use our formula for part A to find the height of the balloon after it reaches 8 minutes. So we can just leave it there, or I could try to take that to a naught. Either works. So we're just taking half the distance, right? So 200 would go to 100, and 100 would go to 50, then that would go to 25, then it would go to 12.5, then 6.25, then 3.125, and then 1.5625. So in 8 minutes, the balloon reaches what height? Well, we just need to add all of these together. Would get us a total of 398.4375 feet. Last example, example 14. Big Tech Electronics advertises a monthly payment plan for the purchase of the best-selling tablet. Buyers pay $50 at the end of the first month. So a sub 1 is 55, or 50. Second month, 55. Looks like third month is at 650. To get my R, we're doing 55 divided by 50, so 1.1. So we want to know fourth. So my fourth month would be 60.5 times 1.1, which would get us 66.55. The sixth month would be, well, 60, so times 1.1 again would get me 73.205 for the fifth month. Times 1.1 again would get me 80.53 for the 6th month. And then the 10th, 6, I'm just doing multiplication over again. 7, 8, 9, 10 would get us around 117.90, depending on how we're rounding it, for the 10th month. So total, how much will a customer pay for the tablet with this payment plan? So my total is going to be equal to A1 plus A2 all the way to A12. So we can either total all of those up. There is a formula that we can use. You guys learned it last year in Algebra 2 to find the sum of a finite geometric sequence. You do your first term minus 1 minus r to the n all over 1 minus r. So my first term is 50 times 1 minus 1 point r, we're going to the 12th, all over 1 minus 1.1. Putting that into my calculator gets us $1,069.21. So we can either use the formula or you could just literally count up the next 12 digits. That would work too. Formula is probably a little bit easier. Write a general formula for the scenario as a geometric sequence and as an exponential. So a sub n is equal to my first times 1.1 to the n minus 1. Or if we wanted to knot it, my a naught would be, so 50 divided by 1.1 is 500 over 11 times 1.1 to the n. So then my function notation would be f of n is equal to 511ths 1.1 to the n power. What does the ratio represent in context in this scenario? Well, 1.1 is the same as 110%. So it means that you are paying your original amount plus an extra 10%, right? So you're paying 10% interest on your balance each month. And that concludes your notes.